So we have learned that we can standardize our data values using the z-score formula when we're dealing with data that is roughly unimodal and symmetric. So we take our data point minus the mean, divide by the standard deviation, or written out this way is our formula. And we learn the empirical rule that 68% of our data lies within 1 standard deviation of the mean, 95 in 2, and 99.7 in 3 standard deviations of the mean. But what if our data values don't fall exactly 1, 2, or 3 standard deviations above or below the mean? Well, then we can use a table of normal percentiles or our calculator in order to look up the percentages that go with those values. So we're going to investigate how to do that now. All right, so in your textbook, you have Table Z and Appendix F. So let me show you really quickly where that is. If we go back over to our textbook, sorry about that, right here. Go over to our textbook, Appendix F. By the way, once you go into my stat lab and go on the textbook, just hit the contents and scroll down to Appendix F right here. Appendix F tables. And so what we see here are the first 2 digits of the z-score. These are the negative ones on this page. And the third digit of the z-score up here. So if I wanted to know the percentile that goes with a negative 2.25, this is negative 2.20, see up in the column it's 0, negative 2.21, negative 2.22, negative 2.23, negative 2.24, and negative 2.25. So our percent that goes with it is 0.0122 as a decimal, so 1.22%. The next page over has the positive z values. So that's what we're doing here with this slide. This is showing you the first 2 digits of the z are here, the last 2 digits, the last digit of the z, the second digit of decimal place is up at the top of the column, and it's always the area to the left of that number that's in the table. Let's look at an example. Suppose women's weights are normally distributed with a mean of 140 pounds and a standard deviation of 29 pounds. Approximately what percentage of women have weights between 143 and 201? So we start by getting the z-scores. So my z-score is going to be my data value, 143, minus the mean over the standard deviation. Well, that's a 0 on the top, so that's a z-score of 0. And my second z-score is going to be the second data value, 201 minus 143 over 29. And so that works out to be 58 over 29, and that's a 2. So if I look at my model here, this is a normal model centered at 143, which is my z-score of 0. And we're going up 2 standard deviations to 201, which is my z-score of 2. And I want to know the data values that go in between that. Well, if you are good with your symmetry skills, then you know from what we discussed before that it should be 34% plus 13.5%, approximately. So that would be 47.5%-ish, but we're going to find it exactly on the table. So let's go over here to our table, and we're looking at a z-score of 2.0, so that's right here, 0.9772. So 0.9772 is all the area from negative infinity up to here, 0.9772. So we want to remove this area, which we know by symmetry is half the curve. So 0.9772 minus 0.5 is 0.4772. So approximately 47.72% of women would have weights in between those values. Now, to do it on the calculator, we would pull up our calculator and we would go into our distribution key. So we're going to hit second and the vars key to bring up the distribution menu. And the normal CDF is the one that gives us the area under the normal curve. So my lower score here, the mean was at 0, and I'm going 2 z-scores up with a mean of 0 and a standard deviation of 1 since I'm on the normal curve. Hit enter, and there's that 0.4772 that we found from the chart. Now, alternatively, I could have instead used the values in the problem and said my lower is 143, my upper is 201, my mean is 143, and my standard deviation is 29. And notice that it gives me the exact same score, 0.4772, because one way I'm just doing it with the normal, with the standardized normal, and the other way I'm doing it with the normal distribution for the weights. So let's suppose that women's weights are normally distributed with a mean of 143 and a standard deviation of 29. Approximately what percentage of women have weights between 140 and 211? All right, so now we're at 143. Standard deviation is still 29. I want to go between 211 and 140. I don't think I drew that quite symmetrically. 140 should probably be closer over here, but you understand what I'm doing. So I'm trying to do this area in between. Okay, so my z-score here would be 140 minus 143 divided by 29. So if I work that out, that's going to be a negative 0.1. And my z-score here would be 211 minus 143 over 29. So again, if I work that out, that's 2.43. So I can look up each one of these z-scores in the chart and then subtract the areas I find for this one from the area I find for this one. Or I can just use my calculator. So again, with the calculator, I can just go second, distribution, normal CDF. We're going to go from 140 to 211 with a mean of 143 and a standard deviation of 29. Notice that doing it this way on my calculator, I don't have to convert the z-scores. We get 0.5317. So we would say 53.17% of women have weights in between those values. Now, sometimes we start with the area and we want to find the z-score or the original data value that goes with it. For example, maybe I want to know what the cutoff point is here for 25%. So I work it backwards. In terms of the chart, I would go over here to the chart and find where the 0.25 is in the center. So looking at this, we see 0.25. Why can't I go down? Need to be able to scroll down, but I don't seem to be able to right at the moment. Okay, so it's going to hurt my eyes looking at this. 0.25, notice is right in here. So somewhere in between negative 0.66 and 0.67. That's the way we would look it up on the chart. So the way that we would do it in our calculator is go back to the distribution menu, but instead of using normal CDF, we use the inverse norm. So for this one, I want an area of 0.25 on the standard normal curve, so mean of 0, standard deviation of 1, and there we see a negative 0.67, just like we saw by looking in the chart. So this just shows us we read the chart backwards. All right, so suppose women's weights are normally distributed with a mean of 143 and a standard deviation of 29. So here's our 143. we want the 10th percentile, so we want the area here to be 0.10 for the 10th percentile. So I'm looking for the score that's down here, that's a question mark, that was supposed to be a question mark, that makes that a 10%. So we go to our calculator. Inverse norm. And we're going to go 0.1, mean of 143, standard deviation of 29. And we get 105.8. So a weight of 105.8 is the 10th percentile. Let's look at another example. Assume body temperatures of adults are normally distributed with a mean of 98.2. So I'm going to go right here and draw my 98.2. And a standard deviation of 0.62. Find the temperature separating people in the bottom 2.5% and the top 2.5%. Okay, so I want this to have an area of 2.5%, so converted to a decimal, that's 0.025, and this would be 0.025. All right, now, notice if this is 0.025, so as a percentage, all the area would be 100%. So as a decimal, 100% is a 1. So all this area under the curve, the whole thing is a 1. So if I want to know everything up to this point, that would equal 1 minus 0.025. That's 0.975. So I'm going to go to my calculator. And we're going to go to the inverse norm. And my area for the first one is 0.025 with a mean of 98.2 and a standard deviation of 0.62. And we get a score of 96.98. Now let's do it again. But this time, for the second data point, I'm going to put in that area 0.975. Otherwise, everything else stays the same. And we get 99.4. So, between 96.98 96.98 degrees Fahrenheit cuts the lowest 2.5%. And I forgot what my other score was. Let's see, 99.4. And 99.4 degrees Fahrenheit is the cut for the upper